So the thing I often hear is that 3D printing isn't very good because when you print something off, it never actually fits. And to be honest, that's very true. I printed this, which is a rotary valve air engine that I liked the look of. I wanted to have a see how it worked and see if we could improve it in inverted commas. But when I printed it off, then I found that the valve doesn't fit in the valve sleeve, the flywheel doesn't fit where it's supposed to go, and the crankshaft certainly doesn't fit where it's supposed to go. I'm going to have to spend time drilling this out, sanding this down, playing with it, probably a few hours, to get the thing to fit. And because nothing fits, then 3D printers are rubbish. Now, I don't agree with that. Actually, I don't think this is a problem with the 3D printer. I think it's a problem, with all due respect to not being meaning to be rude to the designer, I think it's a problem with the design. Now, this was designed as part of somebody's degree program, and they're going to have availability of a workshop. So it was designed with that in mind and produced on lathes and mills and cast. It would be beautiful. Produced on a 3D printer, nothing fits. And that's because it wasn't designed with a 3D printer in mind, and that happens so often. The thing about a 3D printer, or at least the 3D printers we use in home, is they're a tool for a specific job. And if you use a tool wrongly, you're always going to make a mess. I mean, I could use a screwdriver to chop apart a bit of wood. It'd take me forever, I'd have raggedy ends, but I could do it. Or I could take a saw and saw it in two and get a beautiful job. When you're wanting to do a job, then you choose the tool for that job. Now, the designer here, the job they wanted was a perfectly machined air engine. Well, the tool they used to produce that was a home-based 3D printer, so no wonder it's an actual failure. Nothing fits because it wasn't designed with the tool in mind. It was designed with a whole other set of tools in mind. Because a home-based 3D printer, when you think about how it works, it lays down a track of basically molten plastic. The plastic, of course, flows. Then it immediately lays another track on top of it, putting compression on it, and it flows even more. And so we get flow in the plastic where you're not going to be able to get the tolerances that you actually want. This was meant to be cast, milled, and drilled. So even then, it wouldn't have had the tolerances until it went through the machine process. Now, you can get 3D printers that will have tolerances in the order of 1 in 10,000. The only problem is you need a spare 250,000 in order to get them and put them in your home. Most of us are quite lucky to have a spare 250 to buy a home-based 3D printer and put that in the home. And of course, being so much less means that it is not all singing, all dancing, little button to put sugar in your tea. It comes with limitations, and the main limitation is the tolerance of it. So 3D printers can have fantastic tolerance, but home 3D printers that you pay 250 for tend not to. Now, there's a huge amount of development in 3D printers, of course, and they are going to get better and better tolerances and better speeds, probably somewhat rapidly. But just right now, we have to work within the limitation of what we can actually afford. And of course, that means designing with those limitations in mind. So when a designer designs a metal block to be cast and drilled and milled out to be an engine, they design them too big. They design them with the shrinkage in mind and the amount of metal that's going to be cut off in mind when they design the mold. We have to do the same kind of things when we're dealing with a home-based 3D printer. Now, some people might say, well, that's rubbish. In that case, just don't buy one and pay for that kind of engineering. But that kind of engineering comes at a very hefty cost, and it stops you being able to develop your own ideas and get your own ideas into reality, when all you really needed to do was think, well, 3D printers are awesome, but I have to design with them in mind. And that's the whole thing. People seem to be forgetting they're a tool, in the same way that any tool is a tool. Screwdriver's awesome for putting in screws. A saw's not so great for that. So you have to choose the design that you want, or rather make the design that you want with that tool in mind. And here's some examples. This is my water clock. It actually works really, really well from a drip of water feeding in here, rocking the arm backwards and forwards, and of course I've made a video on that. Look at the gears. The gears are absolutely huge. I mean, they're almost a centimetre high. They're almost a centimetre high because the tolerance of my machine is about 0.2 of a millimetre. So if I made my gears 0.2 of a millimetre, the chances are they'll never mesh. Plus it's made out of PLA, so they're going to wear out really, really quickly. With gear teeth this kind of size, then we're going to spread the load. They're always going to mesh and they won't wear out nearly as quickly. So you can make very nice machines if you design with the tool in mind. Of course, not having tight tolerances would mean that you don't get 100% efficiency. Of course not, you lose efficiency because it's not brilliantly tolerant. But that can very often really not matter very much. And something like this is not that important actually. On other things where you're doing wind turbines and generators, then it's questionable if that efficiency is as important as we think. And of course the efficiency of something will go up if you pay for the engineering, but you'll be able to develop what your idea is, prove your concept with a slightly reduced efficiency. And here's another example. This is an epicycloid gear that I made. Again, it's quite large because the size increase means that the percentage of the tolerance decreases in relation to the whole size, and so it becomes more efficient the larger I make it. Making it large also means that I can demonstrate rather easily, and I can always reduce the size, even in some heaven I can never afford the engineering. But I turned this into a generator with surprising efficiency. It was about 98% or so, which is pretty good for something that comes off a 3D printer. So the main idea here is that the takeaway, if you like, is that when you're working with a 3D printer, which is a stunningly useful tool, then design your models with that 3D printer in mind, and you'll get things that go together and work. All the stuff I make goes together and works because I designed that with the printer in mind. Now, some people will say, well, what's the point? If you can't get perfect tolerances, what's the point of getting a 3D printer? And, you know, if what you want is perfection, yeah, you're right. There's no point in getting a 3D printer, but there is no perfection, and so you're probably wasting your time, unless, of course, you have millions to spend. For the rest of mortality, who can put up with designing with those tolerances so that we can get prototypes to show our ideas, to develop our ideas, to create models that work in the real world. A 3D printer is absolutely brilliant. And all that's going to happen is the same thing with telephones and cars. It's going to get better. Anyway, I wanted to talk about that because I so often find that people are doing stuff where they haven't thought about the limitation, and then they're saying, oh, 3D printers aren't very good because of that. I disagree. I think the designer isn't designing with that tolerance, with that model, with that machine in mind. Anyway, I hope you enjoyed the video. Thank you very much for watching, and please do remember to like and subscribe.